Okay, welcome to this next lecture of machine class. That is, we will continue with ideal transformer once again. And in today's lecture, I will develop the equivalent circuit of an ideal transformer and then try to bring into the realities into the ideal transformer one by one. Before that, a brief recapitulation what we have done in our last class. That is, you remember that a ideal transformer has got no resistance, leakage flux, as well as no core losses, and whenever you apply a certain AC voltage across the primary, the induced voltage magnitude in the primary is also same, and it is equal to E1, and there will be induced voltage across the secondary terminal, and no matter whether the secondary is open or closed, flux level inside the core of the machine is constant. In fact, it is because of this that whenever we load the secondary of a transformer, the secondary MMF should be appropriately counterbalanced by the additional current drawn by the primary from the source, and that additional current we will call it I2 dashed, and the secondary current is I2, such that I2 dashed into N1 will be equal to your I2 into N2. I2 dashed is called the reflected current on the primary side. Reflected current. On the primary side, due to current in secondary. In other words, I2 dashed will be, magnitude of I2 dashed will be I2 divided by N1 by N2, and we have already defined the turns ratio to be A, so it will be A. Obviously, in a transformer, we have also shown that E1 I1 is equal to, E1 I1 means I2 dashed is equal to E2 I2. I2 dashed, in this particular case, we can call it to be I1. And there is no distinction between I1 and I2 dashed. The total current drawn from the supply will be I2 dashed itself. So that is the primary current. So we get one very important relationship, that is the volt ampere is constant on both the sides. On both the sides. To give you some idea, suppose you have a transformer whose rating is 100 volt stroke 200 volt, and the volt ampere is 10 kVA. kVA rating of the transformer is this, and it is 50 hertz. From this data, we can easily calculate what maximum current can be allowed to flow through the LV side or through the HV side. By virtue of this relationship, we know that the volt ampere will remain constant. So we can say ILV rated should be equal to 10 kVA, 10 kVA or 10,000 volt ampere divided by 100, which is equal to 100 ampere. Similarly, IHV rated should be equal to same volt ampere divided by 200 here, which will be 50 ampere. So one thing should be understood clearly: if the secondary carries rated current, primary too automatically carries rated current. You need not bother. Because of that mechanism, that is, transformer will always try to cancel off any additional MMF imposed on it by any of its secondary coils. So because of that, the current ratings will be different. In fact, that is why in a transformer, if it is a large transformer and the voltage ratio is quite large, say in the ratio of 100 and 200 like that, 1:2, one can, by looking at the gauges of the primary winding and secondary winding, can decide upon which one is LV side, which one is HV side. Because obviously the HV side rated current will be much lower compared to the LV side when rated condition prevails. Therefore, the cross-sectional wear of the secondary will be much smaller than the cross-sectional area of the primary winding. That is, LV side windings is to be carried out with higher thickness or dia wear compared to the HV side. This we can just understand. Now, just I will tell you one simple problem. Of course, I will not solve, to highlight the case that when a transformer has got a multiple winding, suppose one of which of them will be used as the primary and secondary can have, suppose there are three other coils are there. Suppose the number of turns of this winding which is energized from AC source, let us call it N1. The other three coils number of turns are suppose N2, N3 and N4. Now obviously, if we connect voltmeter across the secondaries of each of these other three coils, there will be induced voltage available. For example, E2, the induced voltage here, should be equal to V1 by N1 into N2. Similarly, the induced voltage in the third coil, E3, should be V1 by N1 into N3, and induced voltage in the fourth coil will be V1 divided by N1 into N4. So all of the secondaries become the source of EMFs or at various levels, and of course at constant frequency, because frequency does not change when you transform the voltage with the help of a transformer. Now, to tell you the implication of the fact that the flux remains constant in a transformer core, no matter whether it is loaded or not. Suppose I have now connected a resistive load across E2 and suppose a inductive load across E3 and a capacitive load across N4. That is, suppose this impedance is XL, this resistance is R, this resistance is XC. Then how can I find out what will be my primary current? That is the problem. So in this case, suppose this is my applied voltage. There is obviously flux induced in the transformer because of very negligible magnetizing current, which I am not showing because it is so small, Im, in an ideal transformer. Then there will be induced voltage in all the windings, where E1, length of E1, will be same as V1, and depending upon the ratios, you will get the voltage induced in E2 and suppose in E3 here. Now let us take one secondary at a time. For example, the N2 turns. Here the current in this one, let us call it some I2 bar. It will be placed here, I2 bar, in phase with E2. Naturally, this I2 into N2 will try to offset the MMF in the core, trying to change the flux level in the core, which of course cannot happen because flux level must remain same in order to satisfy KVL equation in the primary loop. Therefore, the moment I2 flows, there appears a current here, I2 dashed, which I will show it here, I2 dashed. The magnitude of which will be I2 divided by N1 by N2, that is I2 dashed will be I2 divided by N1 by N2. So I2 dashed will flow. Similarly, if it is an inductive circuit connected across N3, the current in this circuit, if I call it I3 bar, it will be lagging E3 by 90 degree, actual secondary current. How much will be its length will depend upon the magnitude of XL, etc. So this I3 once again will produce an I3 dashed here. So the value of I3 dashed, magnitude of I3 dashed will be actual I3 divided by N1 by N3. And similarly, you can get I4 dashed, which will be equal to I4 divided by N1 by N4. So I4 will be leading, so I3 will have a reflected part. Suppose this is I3 dashed. And I4 will be here, leading the voltage E4 dashed. And I4 dashed will be perhaps here, So I2 dashed plus I3 dashed plus I4 dashed will now decide the total current drawn from the supply. So the vector addition of I2 dashed, I3 dashed and I4 dashed will give you the resultant current, and you can find out it. So the MMF balance of the several windings will ultimately give you the current in the primary winding. This you should remember. Now let us come to the equivalent circuit of an ideal transformer. Equivalent circuit of ideal transformer, IT. Now suppose you have got an ideal transformer. With N1, N2 turns, and it is supplied with a voltage V1, supply frequency F, and here will be some load connected Z2 impedance, and there will be current we have seen I2, and there will be some reflected current I2 dashed here. Now look at the supply. Supply really does not know whether you have connected a transformer at its output or not. What it knows is, that is, it sees some impedance connected across its two terminals. Is not. So the point is whether this circuit can be represented as the source V1 and a current I2 dashed it is supplying, and a load is connected right across it. Okay, that is, source will see some impedance connected across it because it is supplying some current I2 dashed. For example, in this earlier thing, if you add I2 dashed, I3 dashed, I4 dashed, suppose the resultant current becomes this one, which I call it I1. Is not this I can find out to the source, and I will find out what is the resultant power factor at which it is supplying this. So to the source V1, what impedance is connected? V1 divided by I1 bar, that is the effective impedance as if connected across the load is V1 bar by I1 bar. Or in other words, across the supply, if you connect this transformer, with various loads connected across its secondary, the supply will react in some way by drawing some current I1 at some power factor angle theta. The same thing will happen if you have this supply and connect it across a load whose impedance is Z effective. The supply will not distinguish between these two things. Are you getting? That is, the question is, supply sees what impedance connected across its. So that can be easily found out in this particular case. For example, in this ideal transformer, we know this thing. See, I2 dashed, magnitude of I2 dashed is how much? I2 by A, where A, you remember, it is N1 by N2. And this is in fact equal to your I1 in case of an ideal transformer. So what is the impedance value the supply will see? Suppose some Z. This will be equal to magnitude of voltage by magnitude of current it is supplying. So this will be V1. Now let us transform this V1 in terms of E2 and I1 in terms of I2. So E2 as we know, it is nothing but V1 by N1 into N2, that is V1 by A. So V1 can be written as A into E2. I1, which is equal to I2 dashed, and this can be written as I2 by A. So this will simply becomes equal to S square into E2 by Z2, E2 by I2, which is equal to S square into Z2. Or in other words, supply will see as if an impedance is connected across its, no transformer is connected, whose impedance value is S square into Z2. What about the power factor angle of the impedance? This will not change because of the fact, if you draw the phasor diagram, this is phi, this is E2, this is I2, this is theta 2, suppose, the power factor angle of the load, that is Z2 theta 2. Where will be I2 dashed? Along the same line here, I2 dashed. What is this angle? Theta 2. And this is your supply voltage V1. So we can say that the supply will see an impedance. I can write it as this for obvious reasons. Instead of writing Z, I will write it as Z2 dashed. That is, we call reflected impedance of the load on the primary side. This one we will call as the reflected impedance. The same way as we have said, I2 dashed is the reflected current on the transformer primary side. So reflected impedance on the primary side. So Z2 dashed, this impedance value will be same thing as Z2. This is important. In fact, any impedance on the secondary side will becomes S square times seen by the supply, where A is the turns ratio of the transformer, N1 by N2. Is that clear? This is the supply voltage V1. Okay. Flux will be 90 degree lagging. Induced voltage will be E2 here. Suppose secondary, instead of connecting purely resistive or purely inductive load, I have connected an impedance whose magnitude is Z2 and angle is theta 2. So where will be that phasor? And suppose lagging power factor plus theta 2. So it will be positioned. I have drawn I2 first. Now I have to draw I2 dashed phasor, which is drawn from the supply. What will be the magnitude of I2 dashed phasor? It will be this length divided by small a. But where it will be positioned? It will be positioned 180 degree away from it. That is the extension of this line, like this. So what this angle will be? Theta 2. Therefore, magnitude of the impedance will be changed to a square times, but the angle with respect to the respective voltage remains same, theta 2. So we can write Z2 dashed will become equal to a square Z2. Now since he has asked this question, let me just clarify one point. You remember, suppose this is a transformer. Okay, ideal transformer. Now, this phasor diagram, perhaps it may slightly disturb you, why you are drawing E2 like this, I2 like this. Let us put this confusion at rest by telling this thing, that suppose this is a transformer. This is the applied voltage you have applied. There will be induced voltage here in this winding, induced voltage there. Suppose E1, E2. And there will be some current I2. Now, in some author draws the phasor diagram in this fashion, and they are also quite right. They say like this: you have applied a voltage here, V1. Okay, V1 is there. This is the flux developed in the core of the transformer, 90 degree lagging. Now, this induced voltage, what will be its time relationship with V1? Suppose you see in an oscilloscope, they will vary together. V1, E1, so far as time is concerned, if you look at those waveforms, they will be in time phase. Similarly, when some current is drawn on the secondary side, I2 will be flowing. There will be a reflected current I2 dashed. Suppose I2 is increasing from 0. What should happen to I2 dashed? It should also increase from 0 in same phase. Then only it can cancel off that MMF. For all the currents, all instantaneous values of the currents, the MMF must be balanced. So what they do is this, while drawing the phasor diagram, they will draw like this. B1 is there. Let us not forget about the direction of the power flow. As I see in the time domain, I will draw like this. This is V1. E1 I will draw like this. E1 straight. E2 will be like this. E2. Secondary current. Suppose lagging power factor. You draw I2. What will be I2 dashed? You draw I2 dashed here only, along this line. Only thing, its length is changed because of the transformation ratio. But strictly in time domain, they are all in phase. Then why people draw such a phasor diagram? They draw it just to show that the induced voltage sense, the voltage induced in the, say, the primary winding, it will try to, if suppose it was allowed to pass some current, it would have pushed out power from the winding to this side. See, any induced voltage, that is, it is in opposition with V1. Just to convey that, they show it 180 degree apart. Similarly, I2 they draw here, I2 dashed they draw here, in order to show that the MMF cancels out. Nothing more to it. Or if you are happy with this, you draw like this. You will get the same results, no problem. Because the EMFs induced in this one will be in time phase with this one, if you look at a oscilloscope. Similarly, I2 is increasing in this way in time. I2-2 will increase really like this. Only thing, its amplitude will be different because number of turns are different. Had it been same number of turns, then the amplitudes would have been equal, so that it can balance of the MMF at each and every instant of time. So anyway, whichever you feel you draw, I don't mind. But I will prefer this one so that the phasor diagram becomes neat now and you can carry on with your calculation. Is that clear? So we found that we were discussing with the equivalent circuit, and we got that any impedance on the secondary side gets reflected to the primary as a squared Z2. Okay. Now, before I proceed further, let us see another interesting thing. Suppose this circuit, this whole circuit involving a transformer, I want to represent it by a diagram which will correctly represent the no load situation as a load situation under loaded condition. I mean, what I mean to say will be clear if I draw this diagram. Suppose I will draw like this. That is, this transformer, suppose it is open circuited. It is connected to a source. This point you just try to understand. This is the secondary winding. This is the primary winding. In actual practice, this is the actual transformer, and suppose you have connected an ammeter here, and here is a switch, suppose. Okay, that is, I will represent it here. There is a switch, and there is a load connected across it, and here is an ammeter connected. Tell me, when the switch is opened, how much the ammeter will read in an ideal transformer? 0. Now, when this switch will be closed, how much this ammeter will read? I2 by A. Actual secondary current by A. Is that clear? Therefore, these windings, what I will do is this. I will show it. So this portion is your really ideal transformer, which does not draw any current under no load condition. And the moment this fellow, the secondary, carries a current, it invites a current here to balance the MMF, like that. Now, let us see. So, this will be the equivalent circuit of the ideal transformer, showing both the primary and the secondary. Now, the same equivalent circuit we can draw by drawing the so this is called the equivalent circuit of the ideal transformer, general equivalent circuit of the ideal transformer. Now, sometimes we say that equivalent circuit refer to primary. Which I have already done. Equivalent circuit referred to primary will be, first I draw, then I will tell. This is V1, and there will be Z2 dashed, which is equal to S square Z2, and this is the supply voltage. This is a very simple circuit. This I call the equivalent circuit referred to primary. That all the secondary quantities are represented on the primary side. And this current I should show what? I can write I1, which is not I2, but I2 by A. That is same as I2 dashed. Or in other words, if suppose in a circuit there are several transformers connected, and suppose they are ideal transformers, you can solve the circuit. Suppose you have been asked to solve this circuit with S closed. What will be the currents in the secondary, primary, like that? What you can do, one option is, you don't bother about referring the equivalent circuit with respect to primary and secondary. You just leave with what it is. You find out the voltage here, find out the current, then I2 by A, like that you can do. Somebody else who knows this one, he will perhaps do like this. Okay, this is the problem, I have to find out this current. I have to solve this simple circuit. V1, there is some impedance connected across it, whose value is S squared Z2. I will find out this current, I1. Then someone may question, what is the secondary you have not calculated? You will tell that is very simple. Once I know I1, I know I2 dash, I know, I can calculate I2 by knowing that transformation ratio. Are you getting? So in this very simple case, it may not sound very exciting. What is so new about it? But this is the way we will be drawing the equivalent circuit of a transformer, of a practical transformer later. So all those simple things, but you should understand what is meant by it. Similarly, obviously, referred to the primary, similarly it is possible to have equivalent circuit referred to secondary. What is the basic idea here? Should we look at the load? Load does not know it receives the power from the output of a transformer or not. It receives power from a source. It is drawing some current at some power factor angle with respect to the voltage connected right across it. That is, with respect to the secondary side, the equivalent circuit will be, the secondary impedance will be there, Z2. I am now sitting on Z2 and trying to identify what is the voltage applied across me. So what should I draw here? V1 by A, correct. Of course, if you now solve this circuit, what you will get? You will get I2. All the actual quantities in the secondary side. Current you calculate. Secondary current. This impedance is the actual secondary impedance. Of course, if someone tells, but your circuit is like this, I2, okay, you have calculated in this simple circuit. What about I1? Then you will tell I1 will be nothing but I2 dash. It will be I2 by A. Over. Getting? So, equivalent circuit of a transformer is sometimes drawn, referred to primary or referred to secondary. Like this. And this is the equivalent circuit of the transformer. Now today I will introduce or slightly complicate the thing by gradually removing one after another the ideal conditions that we have already assumed. That is, we will bring realities into the transformer one by one. Let us remove one of them. That is, suppose towards actual transformer. You can give heading like this. Towards actual transformer. Let us start our journey. Transformer. Not ideal, Not ideal. The first one we will remove is that suppose mu r is finite. Suppose mu r is finite. That is a practical iron material where you cannot have vanishingly small current drawn from the supply and establish any flux you like. That is quite natural. Say the irons which are used for that, mu r is finite. In other words, I will once again go by this one. This is suppose this practical transformer where resistance leakage fluxes are not present, I have assumed, but only mu r is finite. Let us see what will happen. So this is somewhat practical transformer, these windings, and here is Z2, and here is your switch S. Suppose initially S is opened, and here is AC source connected, V1 F. With switch S open, tell me what will be the ammeter reading? Will it be 0 now? No. It will draw some current. How much current it will draw? That how do you find out? I will quickly tell. You see, V1 you have applied, N1 you know, N2 you know. So 5 max I will calculate. V1 divided by root 2 pi F N1. This much flux is to be developed. Then I will calculate B max in the core. I will calculate. Then I will refer to the BH characteristics, which is now like this. Let us assume this is linear. Mu r is finite, but no this thing. So from this I will calculate H, B max. I have calculated. From this I will calculate H max. H max is what? N, that I max by L, length of the core. And I can calculate estimate I max to establish that flux. And that divided by root 2 will give me the ammeter reading. Okay, so N I max you will calculate. So that divided by root 2 will be. That current which is required to establish the flux is called the magnetizing current. So IM is called the magnetizing current, which hitherto we neglected. Magnetizing current. So under no load condition, some current IM will be there. Just for your information, the order of this current may be 2 to 3% of the full load current of a transformer. For example, I have already told you that suppose the rating of a transformer is like this, 100/200 volt, 10 kVA, 50 hertz. Rated current I can calculate. So as a guess value or estimated value, you can say the magnetizing current will be about, suppose magnetizing current on the LV side will be about say 3% of 100 ampere, means how much? 3 ampere. Or on the HV side, how much it will be? 1.5 ampere, 3%. It is some guess values, not exact, but for a well-designed transformer, this magnetizing current is of the order of say 2 to 3% of the rated current. Now, what this implies, LV side magnetizing current, HV side magnetizing current, means if you use LV side as your primary, then it will draw that much magnetizing current. If you connect HV to the source and try to want it used as a primary, then it will draw that much current, because turns are different. It has to establish same flux. Remember that in a transformer, suppose of this rating, you should be very clear about it. Suppose you decide that I will connect LV side as my primary. You listen, 100 volt, I will connect, 50 hertz I will keep. Secondary, that is HV side, I will connect load, if you decide. There will be some flux level established in the core. Is it not? Now suppose I decide I will use HV side as my primary, LV side I will use connect some load. So you apply 200 volt 50 hertz on the HV side, thinking that on the 100 volt side you will connect a load. Tell me, in both these situations, what will be the flux level? Same flux level. Now to establish same flux level, you require a definite amount of MMF, current into N. But N's are not different. So the magnetizing current required will be also in that ratio. Anyway, that is also understood mathematically. Forget about this physical thing. So anyway, this is the magnetizing current, which is about say 2 to 3%. 2 to, of course, this is not fixed value, but it is quite useful in practice. 2 to 3% of the rated current. Of that particular site, which one you want to use it as your primary? That is understood. So this is magnetizing current. Now the question is, suppose this somewhat practical transformer, I want to draw some equivalent circuit the way I have drawn earlier. How should I do it? Okay, now you tell me, if I close this switch, there will be some current I2, there will be reflected current I2 dashed here. What will be the ammeter reading? It will increase now. But what will be the total current drawn from the supply? It will be this IM bar plus I2 dashed bar. IM bar plus I2 dashed bar will be flowing. But I2 into N2 and I2 dashed into N1 will balance them off, and net MMF acting in the circuit will remain once again IM into N1, such that phi max is established. Now, how to model this one? So, no matter whatever is the degree of loading, this one. Now, this particular thing, first I will draw this equivalent circuit, correct equivalent, representing this one. Then we will try to see whether it is really satisfying the no load and load condition of the transformer. First, the general equivalent circuit. I will do like this. This is my supply. V1, supply frequency F. Now, what I will do, I will connect a reactance here, JXM, I will call it. Then to this, I will connect by dotted line an ideal transformer, where there is a load connected, Z2. This is your switch, and this block is suppose an ideal transformer, and this whole thing is your somewhat practical transformer. That is the actual practical transformer, where mu r is finite. Okay. Now let us see whether it satisfies my no load and that is, can I explain the no load operation and loaded condition operation with this equivalent circuit or not. And here is an ammeter connected. With S opened, this is the supply voltage. How much is current drawn this side? 0, because this is an ideal transformer. That we have already seen. So what will be, but this current is, this is no transformer winding. This you must understand. This is some reactance I am representing to take care of IM. This current is your IM, which is equal to V1 by XM, the magnitude of this current. So during no load condition, ammeter will read only Im. Okay. Now you load it. On the secondary, some current flows, which is I2. Where will be I2 dashed? Where should I show? Here? It is this ideal transformer, so this is I2 dashed. So what will be the total current drawn from the supply? Im bar plus I2 dashed bar. That is, what I mean to say is that in a transformer, which is practical, not ideal now, and I have only introduced one aspect of practical thing, that is mu bar is finite. So that transformer can be looked upon as an ideal transformer with some finite impedance, reactance in fact, Xm, connected across its primary. Then I can invoke all the things I have learned in the ideal transformer. So what will be the, I will just quickly draw and finish today because it is time. So what I will do is this one. Suppose you yourself can draw now equivalent circuit, refer to suppose primary. Tell me quickly, this is V1, supply voltage, supply frequency F. The primary quantities, whatever is present, that will not get changed. So Xm is Xm, that magnetizing reactance. So this is called Xm. It is here an ideal transformer. So what is connected here? A square Z2 will be the impedance, and this will be the equivalent circuit referred to primary of the transformer. Will you please draw the equivalent circuit referred to secondary on your own? And today I call it a day, and tomorrow I will continue with this one.